Okay, so great. So welcome to part three of our tutorial with Surratt. So now we will be determining the dimensionality of the data set. So next we'll be using a certain function named called Jack's straw plot. So this function will help to provide a visualization tool to compare the p-values for each PC with dashed lines, also known as a uniform distribution. So the elbow plot is another heuristic method for reading. So this is one where we look at the elbow, where the elbow is located. So in this case, it's around the PC9-10, which in other words, it would mean that there's the true signal which is captured by the first 10 PCs. So this method is based on the percentage of variation. Okay, so let's get to the coding part. PBMC, okay, Jack straw, so that would be the function. PBMC, the original data set we are using, and okay, plus 10, okay, no, replicate, okay, I forgot the equal sign, that's okay, error, oh, I put a V on accident, that's okay. So, yeah, so I noticed in my last, or in part two, I was going a little bit slow, so I'm going to try to go a lot faster in this one. So I'm going to probably cut this part right here. So wait for it to load. Yeah, this usually will take a while. Wow, this is taking a lot longer than I expected. Okay, oh, I can pause. Oh, oh. Pause record. Okay, sorry about that. It seemed I didn't click pause recording, so we'll continue on. So next will be PBMC score Jack straw. This is another function, and dims equals 1:20, and that's good. Whenever it takes a long time for a certain code line to give an output, then I will be pausing it. It seems I did not click the pause button, so yeah, I'm new to recording using the software, so please bear with me. And here it is. Here's the Jack straw plot. You can ignore this warning message. So this will happen when the data set isn't like full in a sense. So let's continue on. And elbow plot. This would be the last one. There you go. As you can see, the beautiful elbow plot right here. And so, yeah, the first line of code, the one with the initial Jack straw one, will always take a while. So you're gonna have to wait for, right here. Well, I actually put a V in this one. That was the error here. So we're okay. So now we're going to cluster the various cells. So we construct a KNN graph-based Euclidean graph, or Euclidean distance. And this, what a Euclidean distance is, it's the geometry of flat or two-dimensional spaces in PCA space using the find neighbors function. So to cluster these cells, we use the find clusters function. This means increased values lead to a greater number of clusters. Satija Lab, the software or the tutorials and the softwares I've derived this through my research. That's the website that I'd recommend using, and so that they suggest that 0.4 to 1.2 typically return a good result for single cell data sets of around 3K cells. Optimal resolution often increases the larger data sets. These clusters can be found through the indent function. Okay, so let's continue on with the find neighbors function. So PBMC, then there's one time. Okay, oops. Okay, going a little bit too fast here. Okay, great. You see the output there, PBMC, MC. So if you're more if you're interested in learning about the other functions or learning more about this, Satija Lab actually has their own set of tutorials, but you have to be careful to make sure you're looking at the most up-to-date tutorials. Like you'll search up, say, find clusters function in the Google 2020, and then it'll show you information about that find clusters function, and it'll basically explain what to do, what it's doing, and I'll like give example code. But the only downside is that it's not a video; it's just like a guide in a way. So as you can see, it tells the number of rows, number of nodes, number of edges, and so it ran an algorithm here and gave us this information. Okay, so PBMC find clusters. Okay, next head, you put head ident. I said indents on accident earlier, so it's actually idents here, and PBMC comma 5, and it gives us this right here. So these are many nonlinear techniques that are provided by Seurat. These include TSNE and UMAP to explore the data set. So that's what we'll be doing next. So let's run a UMAP here, or UMAP. So PBMC, however you wish to say it. I believe that both of them are a correct way to pronounce. And as always, we can ignore the warning. So I'll be pausing it here and resuming it once it's ready. Okay, great. So the optimization is finished, and now we'll be doing dim plot PBMC, comma, dims equals 1, colon 10, enter that error, dims equals 1 equals 10, dim plot PBMC, comma, oh wow, yep, I'm getting mixed up here. That's my bad. Sorry about that. It's actually reduction equals, and then you're giving it a name like this. So I'm not sure. I must have see here. I mixed up, or I combined these two lines of code, and you can see here the beautiful UMAP here and the various clusters here. And so next, you can actually like save this like this, save RDS, and then put the variable name here, and then put a location like that. But I won't be doing that right now. I'll just continue on now. So now there's multiple lines of codes here, multiple lines of code. So I'll just type them down and then explain each one. Okay, so great. So I've actually entered all the code in here, and so I'll go by each one and try to explain it for you guys. So let's start here. This is the first line of code I entered. So that first line of code will find all markers of cluster 1. And then the second line of code will actually find all markers distinguishing clusters 5 from clusters 0 and 3. And then the third and fourth lines of code find the markers for every cluster compared to all remaining cells. And then it reports only the positive ones. And And then the feature plot function visualizes feature expressions on a tsne or tsna. Also, you can either say it as tsne plot or a tsne plot, and it's also known as a PCA plot also. So, and then another function is the do heat map, and that will actually create a heat map for the given cells and features. So we'll be doing that next. Actually, I'd like to show the, I didn't actually show you guys the various visualizations. So this was the feature plot here, and then let me copy this and just show it to you guys real quick. And this is what that one would look like. And this one I'll copy and paste, and you can see this one. So these are all various different visualization methods to help you with your analysis. So I mentioned the do heat map. So this is what we'll be doing next. So we'll be doing the top 10. And if you don't remember what that does, please refer to my earlier tutorial, our earlier part 2. So it'll be parentheses, or not parentheses, percentage sign, and like this. Actually, there should be no spaces. Okay, so now we'll be doing group by cluster, and I'll just copy and paste this. And top underscore n, and then n equals 10, comma wt equals average underscore log. I can put parentheses log fc. That should work out fine. And then now, as I mentioned earlier, the do heat map. This is a function, and so we'd enter it in like this. Top 10 as I'm just double checking. So top 10, but I was originally putting S, but you have to be careful. This is actually a dollar sign. So gene and plus no legend should work. And says there is a unexpected numeric constant do heat map. So let's figure out what my error was. Features equals top. Oh yeah, I don't know, I keep putting spaces here. Yeah, so I accidentally put a space in between the top and the 10. So that was one of my errors. And now it will show us the heat map here. So it'll take a while for it to load. So just let it load. And yeah, I wanted to stretch it out for you guys to actually see everything correct or fully. And like, this is how it would look. The various molecules are listed, and so great. So now so in the above code, we basically plotted the top 20 markers, like this code right here, of the top 20 markers, unless less than 20. In that case, if it was less than 20, we plot all markers. So this was done for each separate cluster. And so now we're down to our final bundle of code. So finally, we will be assigning cell types to the cell type identity to clusters. Sorry, getting a little bit tongue-tied here. So I'm gonna pause it, write down the code, and show you guys what I did. Yep, and as you can see, I did these lines of code. It helped me basically create a UMAP here. And so, yep, this is basically how you would assign cell types to identify to the clusters. And the final thing you can do is do the save RDS here. If you wish to do that, remember you just do the matrix, yeah, or the variable. You put the variable here. So you put pbmc.data or whatever your variable would be, like in other data sets, depending on your variable. Like sometimes I'll put like SDS, like, or no, ADS, and how my naming system works is I would put AD for Alzheimer's disease, because that's what one of my data sets I was working on was, and then S was for Surratt. Yep. So thank you for listening to my tutorial. I gave a little bit of quick tips and tricks There's lots of guides out there, but I found video tutorials to be at a minimum. So I really enjoyed making this tutorial for you guys.